I'll give y'all some louds. So this is our classes of amplifiers. Class A is what? I understand 360 degrees. But basically that term means whatever comes in on the input, we get out. It's just that what we get out is going to have a power gain. Now amplifiers don't create power, right? Y'all understand that? So an amplifier is not, all the amplifier is doing is managing the power that's available from that thing we call a power supply. So class A basically amplifies the entire input signal. No matter what it looks like, it's going to amplify it. Now, how's it going to amplify it? Well, it can amplify the current, it can amplify the voltage, or it can amplify both. But all of them are going to give us a power gain if it's designed correctly. Now, the problem with class A amplifiers, to do that 360 degrees, they have to be biased on all the time. So it means them suckers are sitting there consuming power even though you're not what? You're not doing anything. And then we got that big old collector resistor up there. All the power in that collector resistor does not go to the load. So you got that collector resistor that's eating up power, right? You understand that? So these guys here are very inefficient, but they still give you a good gain. Then we have class B. These guys only amplify 180 degrees of the input signal. So it's either going to be the positive alternation if it's an NPN or a negative side if it's a PNP. But they are what? They're about 75% efficient. And then we got a class C that amplifies less than 180, less than 180. But these guys are up to 95%, almost 100% efficient. But we can't use them in audio. We use them in RF frequency. We'll look at that in a minute. So what's driving the antenna on this is probably a class C amplifier. Because we can do things with a carrier that, since the carrier runs at a constant frequency, we can do things with RF that we can't do with audio. So here's the different classes. So this would be class A. This would be an AB. This is not exactly true. An AB actually uses two A amplifier. Those two class B amplifiers to make it appear like a class AB, right? This would be a class B, this would be a class C, and these are your other ones. But your other amplifiers are basically digital. So in audio or in analog amplifiers, which is what we deal with in this class, then we're dealing with class A, class B, class C, and then an AB amplifier. And here's the load lines. This is what I'm talking about. So once you establish those load lines, so here's our base current. So this takes IB from 0 up to 250 microamps. And then this would be, this amplifier is running off a 12 volt supply. So what you do is you'd put a dot over here when the transistor cuts off. Then over here you'd put a dot when the transistor saturates. And then you draw a straight line through that. Now if it's a class A amplifier, what would you do is you'd try to put, they call it the quiescent point. You would try to bias it in the center. So that way when you put an input signal in, the output signal, so here's the input signal, all it's doing is changing the base current, right? You understand? This is the change in base current. And then once we get that, we just drop a vertical line down, and then we draw that waveform down there, and that's what's going to be on the output. So the input is going, we're looking at current. The output would be varying anywhere between, about 2 volts and 9.5 volts. Now notice class B is here. So class B is biased in cutoff. And then the input signal does what? Class C is biased down here. So class C, if it's a PNP transistor, we'd actually make the base a little bit negative. And then your input signal has to override the negative before it turns it on. And that's what they're showing you. So class A, we try to get it in the center. We do the best we can. Because remember, when we choose those resistors to bias that thing with, we're stuck with industry standards, right? You understand that? So we try to bias that collector voltage in the center as close as we can. If we bias this way, it's going to be biased toward cutoff. If we bias this way, if we bias this way, it's going to be biased towards saturation. If we bias this way, it's going to be biased toward cutoff. And what that means is it's going to limit your input signal. So that means if I biased it down in here, let's say I biased it down here, and then I put the same input waveform, so we would shift it down to here and down to here. Well, what would happen is it would cause the thing to saturate. So what would happen is my output signal would be clipped on the top, and then we'd have this. It'd be clipped on the top, and then it would have that. When we got up to a certain level. Now, as long as we maintained the level below that, it would amplify fine. But if we tried to put a signal in there too high, then the tops would be clipped. If we bias it up here, then we're biasing it towards saturation. So what would happen here? It would work fine for a certain signal down here, but as soon as it got up, what would happen? Well, what would happen? It would clip it on the bottom. And this, if you're listening to audio, that's going to be really rough sound. What we try to do is we try to put it in the center of that load line, right? Does that make sense? Are we going to be able to put it there? What's the odds of me being able to put it exactly in the center? Slim to none. Because we've got to choose standard resistors. So to put it there, this might be a 1,273 ohm, and this down here when I designed it might be a 10,200 ohm. Guess what? They don't have those, so we use standard resistors, and it's either going to move it up toward cutoff, move it down toward cutoff, or move it up toward saturation. So that means eventually when you turn, if it's designed right, if you put enough signal in that, you're going to get distortion out of just about all amplifiers. So usually they limit the actual volume control below of where the circuit's saturated cut off. You could, but every time you put a resistor in series, you're adding cost to. I could use rheostats, and I could set the suckers directly in the center. But what I'm trying to do is I'm going to sell 1,000 of these things, and you want me to come in here and add 30, 40 more cents to every unit. Well, that's a lot of money that either I'm going to lose or my competitors are going to make off. But as long as I design it so it handles my specs, so I come out with specs on it, and I say, well, this is what it can do. And as long as you stay below those specs, you got no problem. If you try to overdrive it, that's where you get into problem. And that's why your big old amplifiers that are really, really designed cost a lot of money. I don't know if you've ever been in stereos or not, but they've got amplifiers out there that you pay thousands of dollars for. And odds are you go out there and you can't, the average person could not tell the difference, right? Y'all understand that? So yeah, you could put resistors in series, and I would, but you'd still be dealing with tolerances anyway. So if you wanted to hit it perfect, you would use a rheostat. Every resistor in there would be a rheostat, and then you could bias that sucker where? Right in the center. But what are you doing now? You're taking an amplifier that might cost $2 to make, and now you make it cost $20 to get it in the center. But as long as you don't overdrive it, understand, even though it's biased toward saturation or cutoff, all that's going to do, you just add another stage. So you go through more stages. Does that make sense? But still, your stages are still relatively cheap compared to trying to bias this thing where in the center. So those are that's a good point. Yeah, you're right. But couldn't you imagine looking in the amplifier, have 15 resistors in series to get a 1,232.3 ohm resistor? So we're going, Class A this shows it in the center, but odds are it's not going to be in the center. We do the best. Sometimes you do really well, sometimes you don't. Normally it's either going to be biased towards saturation or it's going to be biased toward cutoff. But we can get it close, it's real hard to get where. Right in the center. So this is Class A. In fact, this would be common emitter because they show the input and the output out of phase. Class A common collector, the input and the output are in phase with each other, right? You understand that? And this is showing you what we can do with Class A. They don't show the characteristic curves, which would specify the base current that you would put on You can buy what we call, if you were an engineer, you were designing this is what you would this is what you would use right here. Well, the problem is that they don't give the collector characteristic curve so you could do the load drive. They don't give that. So you have what they call curve tracers, which literally does exactly what we just did. It automatically comes up here and it'll draw it up on the oscilloscope for you. And so you can get those. Or you can get a good approximation by using the beta of the transistor. But the problem is the beta is where? All over the place. But once you set up a voltage divider circuit, you lock the beta in for that circuit. So once you lock the beta in there for that circuit, then you could develop the load line. And we know it, so here it's biased below the center, so we would say it's biased toward cutoff. So what would happen is that the tops would clip. If it's on a common emitter, if it's biased toward saturation, then the bottoms are going to clip. Because the bottom is going towards 0, and the top is going towards VCC, right? Does that make sense? And this is where the oscilloscope really comes into play. So this is showing the bottom being clipped. So this is better than my drawing. So notice here's still the AC sine wave, but what happens is it drops down to 0. And when it drops down to 0, now what happens? 0 current, the transistor cuts off, and then the transistor clips it on. It'll clip it on the top, because once the transistor's cut off, you can't get more than VCC out. And of course, on this one, it's biased towards saturation, so this clips the bottom, right? So when it gets up here, once you saturate it, you can't turn the transistor on more than you want to. So this is these really poorly designed transform radios. People come here and crank them up, and it gets really distorted. Your sound gets really distorted because what are you doing? Well, you're either driving in saturation or cutoff. If it's biased in the center, you're still going to do that. So even if I bias it in the center, and I put an input on it like that, what's it going to do? Well, now the tops are going to be clipped and the bottoms are going to be clipped. But that's what we'd like it to do. So you can tell if it's biased in the center. You turn it up and the top and the bottom start clipping at exactly the same time. That tells you that sucker is as close to the center as you can get. But odds are what's going to happen is the top's going to clip and the bottom's going to clip first. And we'll deliberately do this on the amplifier that we just we'll deliberately overdrive it. And we can see, and what we're looking for is VC to be 1/2. If it's greater than 1/2, that means it's biased toward cutoff. If it's less than 1/2, it's biased toward saturation. Which means if we start putting the signal gets bigger, if it's biased toward saturation, the bottom will clip first. If it's biased toward cutoff, the top will clip first. If the top and the bottom clip at the same time, it means that Q point is where? Right in the center. But you can't tell this with a meter. You're going to have a what? Oscilloscope. Usually to troubleshoot these audio amplifiers, you almost got to have an oscilloscope. So this would be a Class B. This is only, but we could have a negative Class B or a positive Class B, right? So a negative pulse I'll be using an NPN transistor. A positive pulse would be using an NPN transistor, and a negative pulse would be using a PNP transistor. And what we do on an AB is we just hook those suckers together, right? And do something about the crossover distortion. This is the Class C. So what Class C would do is Class C, we literally would come over here and we'd put this resistor down here, and this might be a -2 volts. And then I would come over here and I'd have my my transistor. We'll just use a common emitter because it's easiest to work with. And here comes my input signal comes on. Well, the problem is now when this thing goes positive, this thing has got to exceed 2.7 volts to turn that transistor on. So what happens is we get this on the input, on the output we get this. And then it cuts off. And then we get this. and then it cuts off. But you'll see why it's going to be a real narrow thing, because when it cuts on real fast, and we get these pulses like this out of it. Now, what the beauty of it is that in RF, everything rides on what we call a carrier. And what we do is we use, and if you've had AC, this will make sense. If you hadn't AC, you'll see it later on. But we'll just look at Class C amplifiers. Just about every one of them will be the same. We're not going to have to design it. And just about every one of them that you see is going to have this little circuit right at the top. This is what we call a tank circuit. And what a tank circuit is we would charge it up on one alternation, and then when it drops off, it would discharge back into the circuit. So what would happen, even though this is Class C, what we would see when we got over here, let's do it this way. That didn't work out. This gives us an explanation of Class C. So the only time you're going to run into a Class C amplifier is in RF. And what's nice about those things is that they're over 95 or about 95% efficient, right? So what you get out of this thing is that when the transistor starts cutting off, the output would go up, you would charge up the tank circuit, and then when it starts to cut off, the tank circuit would discharge and generate that right there. So what we get out of the thing is we get a nice AC signal because of this guy right there. We call that a tank circuit. And it's got what we call a resonant frequency. In AC, you'll learn a little about those things. But I can take this and I can frequency modulate it as long as it's in the range of this guy right here, or I can amplitude modulate it, and the carrier would not be affected. That makes sense? Now, what's nice about these things is they're around 95% efficient. So they're pretty close to 100% efficient. So it means it don't take any power to run the amplifier. All the power is going to be in the gain, right? You understand that? The power supply is basically not running the amplifier plus running the output. It's also, so this is what we see. So I guarantee you, this guy right here uses a Class C hooked up to this antenna. Really, really efficient. But we can't do audio with this thing, because audio, the frequency on audio is weird. It's all over the place. But carriers, once we set up a carrier, that carrier runs at the same frequency, and we either vary the frequency just a little bit, we call that frequency modulation, or we vary the amplitude, we call that AU. Of course, the most popular now is FM. Well, that's not exactly true. Now look, so this is a Class AB. So what do I do on a Class AB? This would be one Class A that lets the watt come through, the positive alternation come through. This would be another Class B. It's hooked up to the negative supply. It lets the negative alternation come through. So over here, it appears like it's a Class A amplifier. If I didn't know the circuit, I would think it was Class A. So we call this a watt. We call this an AB. This amplifier calls it an AB. The only way you're going to get this is if you combine two Class A amplifiers. I'm sorry, two Class B amplifiers. I didn't catch it. So if you look at almost any stereo, any audio equipment, almost all of them, any audio equipment is going to use an AB output. Now I got a power amp, of course, My wife made me take my stereo down. It's up in the attic now. I bought all my stuff when I was in the thing. But I had a Kenwood amp that you could actually switch it between Class A and Class AD. So if you're listening to really, really low volume, really quick stuff, then you switch it on what? You put it on A. And then if you're listening to real high stuff, you switch it on what? You put it on AD. But here literally it lets you switch it between the two classes of amplifiers. Now, most people wouldn't know the difference. Right? But now basically you know. So if you see any schematic on any amplifier, odds are it's going to be AD. So let's see if we can find a power amp schematic. We need to do the iPod. We need to do those lab too. So let's go to. Oh, I think I've got one stored. Solid state. And don't get scared. I don't know if it'd be in handouts or it'd be in graphics. Let's look at graphics. So this is a power amp. You can see this is an NPN, this is a PNP, there's your glass AD, and then all this stuff down through the line here is just in there too. And we'll explain these diodes here in a minute. This is not, down here, this would be one channel. But if you look, the two channels are mirrored. And what they do is when they come in, they split your left and right channel up. But they're basically not mirror. They are the same circuit. It's just one of them's for your right channel and one on your left channel, right? So that here's your Class B. Here this would be a common collector. Why? Because we're inputting on the emitter, we're outputting on the collector. This would be a common collector. It looks like this one is too. Looks like this one is too. So remember, by the time they hit this guy right here, this is the power amp. This is not the preamp. This is the power amp. So what they're trying to do is get a lot of what? Current in it. Because amplifiers, speakers work off of what? Current. And we'll look at this one in a minute. I think the input comes in. Yeah, here's the right input, here's the left input. This is the common emitter. This is actually what they call a differential amplifier. Unfortunately, we don't have enough time to get on that. You notice the two emitters are connected together. You take the output off the collectors. So this is a bit, we don't have time to get into this. I don't know where we can get into differential amplifiers. And then this right here, I need to figure that out. Strange guy. But we'll look and see what the purpose of these diodes are here. Probably next class. So this is a typical power amp. Now when you troubleshoot, how are you going to troubleshoot? So you got distortion in your left channel or distortion in your right channel or your right channel's not working. Normally when we troubleshoot these, what do we start doing? We start at the output. Start doing what? Moving back toward the input. Until we find a good signal. Basically that's the way it works. So we start on the output, work toward the input. When we find a good signal, of course, you're going to have to use an oscilloscope, right? Then whatever you just went what? Whatever you just went through, that's where your problem is. Okay, so let's do the lab on, we're going to hook this one up. Common emitter amplifier, I think it's lab number 34. So y'all go ahead and take a break while I hook this up.